Welcome to this explainer. Have you ever stopped to wonder why a diamond is just so incredibly hard, while something like copper conducts electricity so seamlessly? Well, it actually all comes down to a highly ordered 3D geometric architecture hidden right inside the material. Today, we're going on a journey through the geometry of matter, and honestly, it's going to completely change how you look at every single piece of metal or even a simple grain of salt. Here's a quick roadmap for us today. First, we'll look at order out of chaos, then dive into the atomic architecture and see how nature handles packing it in. After that, we'll map the crystal, before finally uncovering a really cool plot twist, the power of imperfections.
All right, Section 1, Order out of chaos. Let's look at the foundational differences in solid matter.
Right off the bat, there's this massive contrast between two main types of solids. On one hand, you have chaotic, amorphous solids. Think of things like glass. They totally lack symmetry and they melt really gradually. But then, on the other hand, you have crystalline solids like copper or table salt. These guys arrange their atoms in this strict, highly regular fashion. And because of that, they get immense stability, perfect symmetry, and a very sharp, precise melting point. We actually call them anisotropic, which is a fancy way of saying their physical properties literally change depending on the exact direction you measure them from. How wild is that?
Okay, moving on to Section 2, the atomic architecture. Let's look at how nature actually builds these flawless 3D structures.
So to build a crystal, you really just need to understand two fundamental concepts. First up is the lattice. Think of a lattice kind of like an infinite, empty set of 3D shelves. It's really just an array of imaginary points in space, where the environment around every single point is exactly identical. But, imaginary points don't actually make a physical object. And that is exactly where the basis comes in. The basis represents the actual physical stuff, the atoms or molecules that you're placing onto those empty lattice shelves.
Put them together, and you get the absolute foundational equation of crystallography. You literally just take your geometric space lattice, add your physical basis atoms, and boom, they combine to create the actual crystal structure. It perfectly bridges the gap between abstract geometry and real physical matter.
Now here's the crucial takeaway. You don't need to study a billion individual atoms to understand a whole crystal. You really only need to study its unit cell. The unit cell is basically the absolute smallest geometric building block that still perfectly reflects the entire structure and all the properties of that crystal. Imagine taking this tiny unit cell and just copying and pasting it over and over again in all three dimensions. That translational repetition builds the entire crystal.
And since there are really only so many ways you can create a repeating 3D shape, a scientist named Bravais figured out something amazing. He realized that all possible crystal environments can be categorized into exactly 14 lattices, which fall into just 7 fundamental crystal systems. They categorize them just by measuring the 3 lengths along their axes, A, B, and C, and the 3 angles between those axes. So for example, the cubic system is perfect symmetry. All 3 sides are exactly equal, all 3 angles are exactly 90 degrees. But as you go down the list to, say, triclinic, nothing is equal, 0 matching sides, no 90-degree angles. It's just a beautiful, exhaustive categorization of nature's geometry.
Let's jump into Section 3, packing it in. Let's see just how efficient these atoms can be with their space.
You can really see the physical difference between these atomic arrangements here. Take a look at the simple cubic structure. The atoms are just sitting right at the 8 corners, which leaves some pretty big loose gaps in the middle. But contrast that with the face-centered cubic structure. Not only do you have atoms at the corners, but atoms are also squeezed right into the center of all 6 faces of the cube. Let's break down the actual math of that simple cubic structure, because it's pretty surprising. When you calculate the volume of the actual atoms compared to the total volume of the cube, the packing factor is only 52%. That means in a simple cubic crystal, like polonium for instance, nearly half of the space inside the material is literally just empty vacuum. It is incredibly loosely packed.
But, as we know, matter wants to be efficient. So, if we shift to a body-centered cubic cell, where we keep those corner atoms but shove one whole extra atom right into the dead center of the cube's body, our packing factor jumps up to 68%. We actually see this tighter structure in metals like lithium, sodium, potassium, and iron.
But nature's absolute ultimate packing hack is that face-centered cubic cell we looked at a minute ago. By forcing atoms onto all 6 faces, materials like aluminum, copper, and calcium manage to squeeze atoms into 74% of the available volume. That leaves only 26% as empty space. For spheres arranged like this, that is literally as tightly packed as they can possibly get.
All right, Section 4,
mapping the crystal. How do we navigate these unlimited sets of parallel atomic planes? So to actually talk about these specific planes, material scientists desperately needed a 3D coordinate system. Enter Miller indices. Developed by a scientist named, well, Miller, this is a universal, foolproof method used to designate any flat slice straight through the crystal lattice. It is simply represented by 3 numbers in parentheses, which we call H, K, and L.
Finding these numbers is actually a super elegant little mathematical procedure. Step 1, you just locate exactly where your plane intersects the x, y, and z axes. Let's say it hits at 3, 2, and 1. Next, you just take the reciprocals of those intercepts. Finally, you clear out any fractions by finding the lowest common multiple. This gives you neat whole number Miller indices, like 2, 3, 6. And here's a fun fact. If a plane runs completely parallel to an axis, its intercept is technically infinity, which means its Miller index is exactly 0.
And that brings us to Section 5, the power of imperfections. Time for a bit of a plot twist.
Yep, you heard that right. After all that talk about perfect geometry, in any real crystal, there are always going to be disturbances in the regular arrangement of atoms. These are known as crystal defects, or imperfections. And they aren't mistakes, really. They're just unavoidable realities of thermodynamics. Everyday processes like heating, cooling, or even exposure to high-energy radiation like X-rays are always going to introduce tiny flaws that completely disrupt that pristine geometric lattice we just spent so much time on. These defects can happen right on a microscopic scale, which we call point defects. Sometimes, a single atom just goes missing, creating a vacancy that actually lowers the material's density. In other cases, a totally foreign atom forces its way in or even replaces a parent atom entirely, kind of like sneaking copper atoms into pure gold. And rather than just being some trivial chemistry fact, these single-point flaws cascade upwards. They can completely change a material's electrical resistance and mechanical strength.
Now, defects can also stretch across a whole line. Take an edge dislocation, for example. Imagine wedging an extra half plane of atoms right into the middle of a perfect crystal, sort of bowing the whole thing outwards. Or, atoms can be displaced to form a screw dislocation. This actually twists the crystal to form a continuous spiral ramp, almost like an atomic spiral staircase.
So what does this all mean? The absolute crucial takeaway here is that real materials are defined not just by their perfect geometry, but by their flaws. Material scientists intentionally introduce defects to change how metals bend or how semiconductors conduct electricity. Which leaves us with a final thought to chew on. If pure, perfect crystals don't actually exist in nature, how can we continue to intentionally design these flaws to engineer the super materials of the future? Thanks so much for exploring the hidden geometry of matter with us today.